Welcome, and we are going to look at the properties of derivatives now and what they can tell us about a curve. And so the first thing we're going to see by the way of studying this behavior of the shape of a curve is called the mean value theorem. And this is not to be confused with the intermediate value theorem, which we saw already. And so you can see the definition of the theorem here. But we have to have a differentiable function on an interval. And then notice the language here. It says there exists a c. It doesn't say what it is, but it says there is one, much like the intermediate value theorem, between a and b, such that if we look at the derivative of the function at this value c, that is the same as effectively the average rate of change. So this is saying at some point on the interval, the instantaneous rate of change is equal to the average rate of change. Okay, and you can rearrange it and play with algebra, multiplying by b minus a to both sides if you wish. Okay, so the idea here, just to put this in a picture form, is that if we have our function, okay, here's a, here's b, and here is f of a, so we have something like this, and I'm just going to draw it in the increasing case. It doesn't much matter if it's increasing or decreasing, but we have a function like this, and then it does something. Let me draw that a little better. Something like that, okay? And if we look at this value c, and and actually before I look at c, so I want to draw the average rate of change, which would be the slope of the secant line that connects these 2 points. Okay, so this is our secant line, and its slope is the average rate of change. Okay, then if I look at c, and I'm just going to pick, say this point, so this would be c. Then if I look at the slope of, or the instantaneous rate of change at that point, and the slope is the instantaneous rate of change here, also known as f prime of c, the instantaneous rate of change at this point c is the same as the secant line slope. Okay, so that's kind of interesting. Let's get some more practice with this. Okay, and so we have a function. We want to find value c in that interval such that the instantaneous rate of change is the same as the average rate of change on that, or we want to show that it doesn't exist. Okay, so it might be prudent for us just to write f of x in a different form, an expanded form. And if we do that, we get x cubed plus x squared minus 2x. Okay, and so now with this, I can start to look at the what the mean value theorem would say. And so to do that, I would maybe take the derivatives of 3x squared plus 2x minus 2. Okay, and so then if I identify that there is some point c in here, I would have f prime of c equaling this 3x squared plus 2x minus 2. Okay, and so that should all be c's, I'm sorry. Let's change those to c's, and now I look at, so this is the instantaneous rate of change. The average rate of change would be f of, and then 2 minus f of minus 2 all over 2 minus a negative 2. Okay, and so the denominator is 4, and then the numerator, if you calculate it out, it's going to be 8 minus 0, and this is equal to 2. Okay, so then if the mean value theorem applies, then we would be able to say that 3c, so mean value theorem would say that 3c squared plus 2c minus 2 is equal to 2, and rearranging 3c squared plus 2c minus 4, and if I factor this, then I get 3c minus 2, and then c plus 2 is equal to 0. So then c is equal to 2/3 and minus 2. And I'm done, right? No. So remember that c must be in the open interval -2 to 2. Okay, so I have to exclude this one, and therefore c is equal to 2/3 is the only value or the only x value such that the instantaneous rate of change is the same as the average rate of change of f on this interval.